You know, every single time you pick up your phone or use your computer, you're interacting with a microchip. But behind that tiny, powerful piece of silicon, there's this massive kind of hidden story, and it's all about water. So let's dive right into this really surprising journey of semiconductor wastewater.
So we all love our digital world, right? But have you ever just stopped and wondered, what's the hidden cost of all this? It's a question that takes us out of those super sterile, high-tech clean rooms where chips are made and into a much, much messier reality.
And here's the answer. It's measured in water. And I mean a lot of it. You see, making just one single microchip can take thousands of gallons of ultra-pure water. It's used for everything: etching, cleaning, plating. And what comes out the other end? Well, it's this incredibly complex and toxic cocktail that you definitely can't just pour down the drain.
Okay, so this brings us to the very first and maybe the most critical stage of the whole cleanup. Before you can even think about treating this water, you have to sort it. This isn't just one big vat of dirty water. It's a whole collection of very different and very hazardous liquids.
And what's so fascinating is when you look at how the problem gets broken down. You can see right here, each part of the chip-making process creates its own unique wastewater. The plating process? That gives us nasty heavy metals like copper and nickel. The etching and cleaning? That leaves behind some really corrosive fluoride. Each of these streams is so different, they have to have their own dedicated treatment line.
And here's the thing you absolutely have to understand. If you were to just mix all of this stuff together, you'd basically create a chemical nightmare. It would be almost impossible to treat effectively. So segregation isn't just a good idea. It is the absolute key to the entire process. Think of it like triage in an ER. You've got to sort the patients before you can start the treatment.
All right, once everything is sorted, each stream is sent off to face its own specific challenge. This next stage is what I like to call the chemical gauntlet. This is where pure chemistry is used to literally pull the most dangerous stuff right out of the water.
So first up, we've got the fluoride stream. How in the world you get rid of something that's totally dissolved in water? Well, you force it to become undissolved. By adding a chemical like calcium hydroxide, you kick off a reaction that makes the fluoride grab onto the calcium, forming these teeny tiny solid particles. But they're microscopic, so to get them out, another special chemical called a flocculant is added. It basically acts like a giant chemical magnet, grabbing all those tiny solids and clumping them together into something you can actually remove.
So yeah, this clumping process creates these bigger, heavier masses. They're called floc, which can finally just settle to the bottom and be filtered out. It's a really clever and totally critical step for separating the solid gunk from the now much cleaner water.
Meanwhile, over in a completely separate treatment line, that water from the plating process is going through its own ordeal. The main target here is those toxic heavy metals. We're talking copper, nickel. The solution is something called alkaline precipitation. By making the water more alkaline, you force the dissolved metals to transform into solid metal hydroxides, which, just like the fluoride solids, can then be separated out.
Now, even after all those heavy-hitting chemical treatments, there are still some really tricky pollutants left over. And to deal with these, engineers turn to a pretty unlikely hero: microbes. Yep, that's right. Welcome to nature's very own cleanup crew.
This line of treatment is going after stuff that's way harder to remove with just simple chemistry. We're talking about organic solvents, sticky flux residues from soldering, and just the general organic pollution that's measured as something called COD and BOD. Oh, and this stream also gets the factory's regular domestic sewage mixed in. Fun, right?
And the solution for this mess is just brilliant. The water is pumped into these huge tanks, or biological reactors, that are just teeming with specialized microorganisms. And for these little pollution-eating microbes, it's literally an all-you-can-eat buffet. They just happily munch away on all that organic waste, breaking it down into harmless things like water and carbon dioxide.
Okay, so at this point, all three streams have been treated on their own and are finally clean enough to be combined. But believe it or not, the journey isn't over yet. Now it's time for the final polishing, a stage that really transforms this water from just being treated waste into a genuinely valuable resource. So, this combined stream of water first flows through these huge sand and activated carbon filters, which catch any last little particles. Then, it's pushed through these incredibly fine membranes, using a process you've probably heard of, reverse osmosis, which can pull out even the tiniest dissolved impurities. And for the grand finale, a blast of powerful UV light acts as a final safety net, zapping any microbes that might have somehow survived the journey.
I mean, the transformation is just incredible, really.
What started out as this hazardous industrial byproduct, totally unsafe for the environment, is now clean water. Water that meets super strict environmental standards. It's gone from being waste to being a reusable resource. And when you look at the actual numbers, the results are pretty staggering.
So, just how effective is all this? Well, let's take that fluoride. The final concentration drops to less than 5 milligrams per liter. That is well within the safe discharge limit.
And what about the biological oxygen demand, that key measure of organic pollution? It's now under 20. That just goes to show you how good those hungry little microbes are at their job. And maybe the most impressive number of all, the final concentration of all those heavy metals is less than 1 milligram per liter. These dangerous toxins have been almost completely wiped out. So, the water is this clean. What happens to it next?
Well, this is the best part. A huge portion of it is now totally safe to be discharged right back into the local river system. But a pretty big chunk is also recycled and pumped right back into the factory. It's used for things that don't need ultra-pure water, like cooling towers or exhaust scrubbers. It completely closes the loop, and that massively reduces how much fresh water the factory has to pull from the environment in the first place. Of course, all those pollutants didn't just disappear into thin air. They've been concentrated down into solid sludges. You've got the calcium fluoride, the metal hydroxides, and the leftover microbes. All of this gets dewatered to shrink its volume, and then it's hauled off by licensed professionals for safe and final disposal. Which kind of brings us to a final big thought. This whole incredibly complex process, it takes a dangerous waste stream and turns it into a reusable asset. It's a perfect example of what we call circular engineering. So it really makes you wonder, as our technology gets more and more powerful, is this kind of responsible, intelligent design the true future of it all?